Have you ever looked up at the night sky and wondered if we're truly alone in the universe? Well, you're not the only one. For centuries, humanity has dreamed of finding life beyond Earth. And thanks to incredible advancements in technology, we're closer than ever before to answering that age-old question. Today, we're diving into the fascinating world of exoplanets, planets that orbit stars other than our own sun. Specifically, we're going to explore some of the most promising candidates for habitable exoplanets, worlds that might just have the right conditions to support alien life. So, what exactly is an exoplanet? Simply put, it's a planet that orbits a star other than our sun. Until the 1990s, we only knew about the planets in our own solar system. Now, thanks to incredibly clever scientific instruments and methods, we've discovered thousands of exoplanets. But how do we find these distant worlds when they're so incredibly far away and faint? Well, there are a few primary methods. The Doppler effect, radial velocity. Imagine a star with a planet orbiting it. The star actually wobbles slightly due to the planet's gravitational pull. This wobble causes the star's light to shift slightly towards the blue end of the spectrum when it's moving towards us, and towards the red end when it's moving away. Scientists can detect these tiny shifts to infer the existence of a planet. The transit method. This is like looking for a tiny shadow. When a planet passes in front of its star, it blocks a tiny bit of the star's light. By measuring these dips in brightness, we can figure out the planet's size and orbital period. Direct imaging. This is the most challenging method as it involves directly photographing the exoplanet. Stars are so much brighter than their planets, making this like trying to see a firefly next to a searchlight. But with advanced telescopes and clever techniques, we are starting to capture direct images of some exoplanets. Missions like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS, have been instrumental in discovering thousands of exoplanets using the transit method. And now, the James Webb Space Telescope, JWST, is revolutionizing our ability to study exoplanet atmospheres, searching for potential signs of life. Okay, so we can find exoplanets, but what makes one habitable? The key concept here is the habitable zone, often called the Goldilocks zone. The habitable zone is the region around a star where the temperature is just right for liquid water to exist on a planet's surface. Too close to the star, and the water would boil away. Too far, and it would freeze solid. Liquid water is considered essential for life as we know it. Think about our own solar system. Venus is too hot, Mars is too cold, but Earth is just right. Its location within our sun's habitable zone has allowed liquid water to exist for billions of years, giving rise to life. However, the habitable zone isn't the only factor. We also need to consider things like the planet's size and mass, its atmosphere, its rotation, and the type of star it orbits. Different stars have different habitable zones. A smaller, cooler star, like a red dwarf, will have a much smaller and closer habitable zone than a larger, hotter star like our sun. All right, let's dive into some specific examples of potentially habitable exoplanets, and we're going to start with one of the most exciting, Proxima Centauri b. Proxima Centauri is our sun's nearest stellar neighbor, only 4.2 light-years away. And in 2016, astronomers confirmed the existence of a planet orbiting it, Proxima Centauri b. This planet is a bit larger than Earth and orbits its star much closer than Earth orbits the Sun. In fact, a year on Proxima Centauri b is only about 11 Earth days. The big question is it habitable? Well, it's located within Proxima Centauri's habitable zone. However, Proxima Centauri is a red dwarf star, which presents some challenges. Red dwarfs are much smaller and cooler than our Sun. They also emit powerful flares, bursts of energy that could potentially strip away a planet's atmosphere and make it inhospitable. Plus, Proxima Centauri b is likely tidally locked, meaning one side always faces the star, leading to extreme temperature differences between the two sides. Despite these challenges, what's even more exciting is that 3 of these planets, TRAPPIST-1, E, F, and G, are located within the star's habitable zone. This means they could potentially have liquid water on their surfaces. These planets are all relatively close to each other, and simulations suggest that they might even experience significant tidal heating from their star and neighboring planets, which could contribute to volcanic activity and a dynamic environment. TRAPPIST-1e is particularly interesting because it has a density similar to Earth's and might have a rocky composition. Scientists believe that it could be the most Earth-like planet in the system. The TRAPPIST-1 system is a prime target for the James Webb Space Telescope, which will be used to study the atmospheres of these planets and search for potential biosignatures, signs of life. Let's head back to the Kepler catalog, where we find Kepler 186f, located about 500 light-years away. This exoplanet was the first Earth-sized planet discovered in the habitable zone of another star. Kepler 186f orbits a red dwarf star, Kepler 186, and is about 10% larger than Earth. We don't know much about its atmosphere or composition, but its size and location within the habitable zone make it an intriguing candidate for habitability. Because it orbits such a dim star, the light coming from Kepler 186 would only be similar to an early sunset, possibly affecting the vegetation on the planet, making it appear more red than green. One fascinating thing about Kepler 186 is that its star is much dimmer than our Sun. This means that any potential life on the planet would need to adapt to lower light levels. Some scientists have speculated that plants on Kepler 186f might be black to absorb as much light as possible. While Kepler 186f is a promising candidate, it's important to remember that it's just one piece of the puzzle. We need more data about its atmosphere and composition to determine if it's truly habitable. Let's not forget about Kepler 452b, located about 1,400 light-years away. It was initially dubbed Earth 2.0 when it was discovered, back in 2015. It orbits a G-type star similar to our Sun, only older. Kepler 452b is about 60% bigger than Earth and is located within the sun of its star. However, we cannot be sure that it is rocky. One of the most interesting aspects of Kepler 452b is that it has been orbiting its star for about 6 billion years, longer than Earth has been around the sun. This means it could potentially have had more time for life to evolve. However, the planet might be entering a runaway greenhouse effect. Unfortunately, Kepler 452b is relatively far away, making it difficult to study in detail. But it remains an important reminder that Earth-like planets can exist around Sun-like stars. Another promising exoplanet discovered by TESS is TOI 700d, located about 100 light-years away. This planet orbits a small, cool M-dwarf star and is located within the star's habitable zone. What makes TOI 700d particularly interesting is that it is a rocky planet, and simulations suggest that it could have liquid water on its surface. One possibility is that TOI 700d could be tidally locked, meaning one side always faces the star and the other side is always in darkness. However, atmospheric models suggest that a thick atmosphere could help distribute heat and make the planet more habitable. You've probably noticed that many of the potentially habitable exoplanets we've discussed orbit red dwarf stars. While these stars are abundant in our galaxy, they also present some significant challenges for habitability. As we mentioned earlier, red dwarfs are prone to powerful flares, which can bombard planets with harmful radiation. They are also much smaller and cooler than our Sun, which means that planets need to be much closer to them to be within the habitable zone. This can lead to tidal locking, where one side of the planet always faces the star. Despite these challenges, some scientists believe that red dwarf planets could still be habitable. A thick atmosphere could help protect the surface from radiation and distribute heat. And who knows what kind of unique adaptations life might evolve to thrive in such an environment. Finding a planet in the habitable zone is only the first step. The next challenge is to determine if the planet actually has evidence of life. This is where the James Webb Space Telescope is revolutionizing our ability to search for biosignatures in exoplanet atmospheres. By analyzing the light that passes through a planet's atmosphere, JWST can identify the chemical compounds that are present, giving us clues about the planet's composition and potential for life. Non-biological processes can also produce these signatures. We call them abiotic processes. Volcanoes, geological activity, even just the way light interacts with certain molecules can mimic biosignatures. That's why scientists are so careful to rule out false positives. It's crucial to understand all the possible non-biological explanations for a signal before claiming to have found life. A claim of a biosignature needs to address every other possibility. Finding definitive evidence of life is like solving a cosmic puzzle. We need to combine observations from multiple instruments, understand the planet's environment in detail, and have a very solid understanding of both biology and geology. The field of exoplanet research is constantly evolving. New telescopes and missions are being developed that will allow us to discover and study exoplanets in even greater detail. One exciting future mission is the Nancy Grace Roman Space Telescope, which will be able to survey a large number of exoplanets using gravitational microlensing. And of course, the search for extraterrestrial intelligence, SETI, continues, with scientists listening for radio signals or other signs of technological civilizations. Looking further into the future, some scientists are even exploring the possibility of interstellar travel. While it's currently beyond our technological capabilities, breakthroughs in propulsion and other technologies could one day make it possible to visit exoplanets in person. But there are ethical implications to interstellar travel. For example, what gives us the right to impose ourselves on another civilization? We could inadvertently introduce diseases, disrupt their culture, or even destabilize their society. Think about the historical precedent on Earth: colonization, exploitation. Do we want to repeat those mistakes on a cosmic scale? And what about the potential risks to us? We could encounter a hostile or technologically superior species. Are we truly prepared for that? Furthermore, the resources required for interstellar travel are astronomical. Shouldn't we be focusing on solving problems here on Earth, climate change, poverty, inequality, before venturing into the unknown? These are uncomfortable questions, but vital ones. The pursuit of knowledge and exploration is fundamental to our species, but we need to proceed with caution, humility, and a deep understanding of the potential consequences. So far, we've focused on planets that are similar to Earth. But what if life could exist in entirely different environments? What if life doesn't need liquid water? Some scientists have speculated about the possibility of life based on different chemistries. For example, silicon is similar to carbon and could potentially form complex molecules. Ammonia or methane could serve as alternative solvents to water. Think about Titan, Saturn's largest moon. It has lakes and rivers of liquid methane on its surface. Could life exist in this exotic environment? We don't know for sure, but it's an intriguing possibility. Think about Titan, Saturn's largest moon. It has lakes and rivers of liquid methane on its surface. Could life exist in this exotic environment? We don't know for sure, but it's an intriguing possibility. The universe is vast and diverse, and it's possible that life could exist in forms we can't even imagine. We need to be open to the possibility that life beyond Earth might not look anything like life on Earth. As we explore the possibilities of life beyond Earth, it's important to consider some of the challenges and paradoxes we face. One of the most famous is the Fermi paradox. Where is everybody? Given the vastness of the universe and the billions of potentially habitable planets, why haven't we found any evidence of extraterrestrial civilizations? One possible explanation is the Great Filter. The Great Filter is a hypothetical barrier that prevents most life from evolving to a certain stage of development. It could be a difficult step in the origin of life, the evolution of intelligence, or the development of advanced technology. If the Great Filter is behind us, it means the discovery of extraterrestrial life would be one of the most profound events in human history. It would change our understanding of our place in the universe and our relationship to the cosmos. It could also provide us with new insights into the origin and evolution of life, and potentially lead to new technologies and scientific breakthroughs. But perhaps the most important reason to search for life beyond Earth is to gain a deeper appreciation for the preciousness and fragility of life on our own planet. By studying other worlds, we can learn more about what it takes to make a planet habitable and how to protect our own planet from environmental threats. The search for life beyond Earth is a journey of discovery that could transform our world in ways we can only imagine. That's all for today's exploration of potentially habitable exoplanets. I hope you found it as fascinating as I do. Which of these planets do you think is most likely to harbor life? Let me know in the comments below. Don't forget to like this video if you enjoyed it, and subscribe to the channel for more space and space-related content. Thanks for watching.